Okay, so today we'll talk about complex reaction. So this is the second chapter taken from James E. House, Principle of Chemical Kinetics. So first I want like to tell you what is meant by a complex reaction. So complex reaction are actually those reactions whose mechanism comprises or composed of more than one elementary steps. So either these kind of reaction they are taking place in many steps, or uh, uh, these reaction the reactant go into product in more than one path. This is actually a typical plot of concentration versus time. So when we have reactant, so at the start of the reactant has highest concentration, and with the passage of time the concentration of reactant is decreasing while the product is increasing. So we have in this case, in this general case, we have product B and product C. So the concentration of product B is increasing with the passage of time. At the same time, the concentration of product C is increasing with the passage of time, and the concentration of reactant is decreasing. So here we have to take a very general example. Second order reaction in which the two reactants are different from each other. So the reaction is actually first order in two reactants, and the overall order of this reaction is second order. So what is meant by a second order reaction? A reaction whose rate is proportional to the concentration of two reactants product raised to first power. Consider a model second order reaction. For example, A combined with B, and it is giving us products. So the rate law for this reaction is differential of reactant A with respect to time is equal to differential of reactant B with respect to time, and this is proportional to the first power of the product of two different reactants. So the initial concentration of A and B when the time is 0 second, so is represented by A. For example, A initial concentration is at 0 time is A naught. Similarly for B, the initial concentration is represented by B naught. Similarly, the final concentration of A and B at time is t any second, 5 second, 10 second, or 20 seconds. So the concentration of A is represented with A. Similarly, how much amount of A will be remaining after any time t. So this will be initial concentration and the concentration of A left. So this is actually the amount of A reacted after any time. Similarly, the concentration of B used or reacted after any time t is B naught, initial concentration minus B remaining. So this is the reactant concentration consumed. So assuming that reactant A and B are present in equal stoichiometric amount in the reaction mixture, so the concentration of A consumed is A naught minus A, and similarly the concentration of B consumed is equal to B naught minus B. So we assume that both are used in equal amount. So solving this for the final concentration of B and putting this value of the final concentration of B in equation 1 in the Redla equation, so we will get the Redla equation by putting the final concentration of B. After rearranging this equation, we will get the Redline equation 3, and in this equation 3 the denominator can be solved by using method of partial fraction, and the general formula for the method of partial fraction is this. For example, if you have x over x plus 4 into x minus 7 is equal to this can give us a over x plus 4 plus b over x minus 7. So solving the same denominator by using partial fraction method, so we have this c1 over a plus c2 over b naught minus a naught plus a. Just putting this value of denominator in equation 3, so we'll get equation 5, and after rearranging of this equation 4, we will get this equation 6. So this is just taking the LCM of this denominator, and after solving, so we will get this equation 6. And equation 6 is actually the same equation as equation 4. The left hand side can be compared, and in the left hand side you can see the denominator is the same is in equation 6. So when the denominator cancel with each other, we have only this one left here, or you can compare, it's very easy. After multiplying with C1, because C2 is already multiplied here, this is plus sign. After a long time, if the reaction goes for a long time, infinitely long time, so the concentration of A, final concentration remaining will be 0, because all of the A is converted into product, no reactant remaining. So by just putting this A 0 in this equation, so these two terms will be equal to 0, and we have only this term remaining. This equation is valid only when the concentration of A is approximately 0, that is, this A is equal to 0. But this equation, the concentration of A can't be 0, because at any instant time some amount will be remaining. So just rearranging this one, and this equation will be valid only when we have this, because the product is 0, so A is not is equal to 0. If A is not is equal to 0, then something should be equal to 0 in order to make this equation is equal to 0. So this C1 constant, summation of these constants C1 plus C2 is equal to 0. Or rearranging this one, so we have C1 is equal to minus C2. This is this equation, taking this equation 7, just taking this constant common, and from this equation we can calculate C1. So this is C1 value, and C2 is actually opposite, with opposite sign, same value with opposite sign, putting the value of C1 and C2 in equation 5. So if you put the value of C1 and C2, so because C1 is just 1 word, this we have this value here was C1, and putting the value of C1, and this also C2 is just with opposite sign, so we have negative sign instead of plus sign in this equation. You can see the equation 5 here, we have this plus sign, so we have to put the value of C1 and C2 is negative sign, so this is the same negative, we have to not change that one. After multiplying with negative sign, so we have this negative positive, this will be negative, this will be again negative positive, so we have negative positive positive. So we integrated this equation between limits, that is initial limit of A, final limit when time is 0, final initial limit of B, final limit of B. We know that this final concentration of B is equal to this term here in denominator. So just taking the common out of integration sign and integrating this first term between limits, initial limit, final limit, similarly plus this second between initial limit, final limit. We just put this value here, and we just change this sign because we have now the differential term B inside integration, and this is the time, initial time, final time. So this can be solved by using the general formula. If we have this 1 over x dx is equal to log x, so this will be equal to log x. So this is constant, and this is final log of final concentration minus initial concentration plus this constant log of final concentration minus initial concentration is equal to kT. Or just rearranging, taking this common because it both has the same common. So just combine, we can combine the plus sign in term of log is multiplication factor kT. So we have this equation, we got this equation. This is the final second order mixed equation. In this equation we already know that the initial concentration can be represented with A, small a, in the final concentration with the A minus X is the amount of product pump at any time. Similarly, initial concentration of B represented with B. Final concentration of B minus X. Just putting these value in this equation, so we have to we will get this equation, and after just reversing this log term, so when we reverse this, we are getting negative sign, and in the negative sign we multiply with this one, so we have actually this reverse A minus B, and this is denominator will go to numerator, so this will just reverse, and this is some kind of equation. This is some kind of equation, a straight line equation, y plus c is equal to mx. So we have only two variable, y is equal to this log term log a minus x over b minus x, and this t is x. So when we plot log term, that is y versus x, log term versus time, so we'll get a straight line with intercept is equal to log a b over a, and slope is equal to k a minus b, because the t is already variable, or from the slope we can calculate the value of k. So this is a straight line equation, and this is the plot of this kind of reaction, complex reaction. Example of this complex reaction is hydrolysis of ester. So this is an example, very simple example, very common. Ethyl acetate hydrolysis. So ethyl acetate react with water, we are getting acetic acid and ethyl alcohol. This is a second order mixed reaction. So please try step by yourself, and if you have any question, please don't hesitate to ask.